Hi everyone! First, I would like to thank the opportunity. It's a great pleasure for me to be here presenting to you. My presentation is about the constant deformations of functions on ICES. This is a work with Professors Bruno F. Sokamoto and Jonivaldo Tomazello, both from Universidade Federal de São Carlos, UFSCar. Let's go! Given F a holomorphic function germ with isolated singularity, if we consider a deformation capital F of f defined by capital F of Tx equals Ftx, then we have the family Ft defined on Cn to C. So we have the following question about this family. When the family Ft has constant topological type, for n equal 3 it's an open problem, and for n different 3, Ft has constant topological type if and only if the Milnor number of Ft is constant. So we can see the importance of studying the constants of the Milnor number of the family Ft. But it is difficult to determine when the family Ft has constant Milnor number. In 1986, Groyle characterized the constants of the Milnor number of the family Ft. More precisely, he proved the following result. Let F be a holomorphic function germ with isolated singularity defined on Cn. For any deformation capital F of f defined on C times Cn, the following statements are equivalent. 1. Capital F is me constant. 2. For every holomorphic curve gamma defined on C to C times Cn, the usual valuation of partial derivative of capital F with respect to t composed by gamma is greater than the infamous of usual valuation of partial derivative of capital F with respect to xi composed by gamma for I equals 1 until n, where the usual valuation in our case is the multiplicity of the curve. 3. The usual valuation of partial derivative of capital F with respect to t composed by gamma is greater than or equal the infamous of the usual valuation of partial derivative of capital F with respect to xi composed by gamma for I equals 1 until n. 4. Partial derivative of capital F with respect to t belongs to the integral closure of the Jacobian ideal J. That is, J is the ideal generated by partial derivative of capital F with respect to x1 until partial derivative of capital F with respect to xn. 5. Partial derivative of capital F with respect to t belongs to the radical of J. And the last item, the variety of J equals C times 0, where the variety of J is the set of points Tx belongs to C times Cn, such that all generators of J in these points equal 0. Given X, a germ of analytic variety in Cn, and F a function germ defined on Cn to C, we have the Bruce-Roberts number of F with respect to X. This number is the dimension of the ring On over the ideal JF theta X, where theta X is the On module of vector fields in Cn which are tangent to x0, and JF theta X is the ideal generated by dF Kc such that Kc belongs to theta x. Replacing J by JFT theta x, Ahmed, Ruas, and Tomazello studied a version of Groyle's theorem for the Bruce-Roberts number, and they proved that 2 implies 3, 3 is equivalent to 4, 4 implies 5, 1 implies 6, if the set C of the points Tx belongs to C times Cn, such that d capital F of Ci of x equals 0 for I equals 1 until p is a Cohen-Macaulay variety, then they proved that 6 implies 1. And if x0 is an isolated hypersurface whose logarithmic characteristic variety LCX is Cohen-Macaulay, then they proved that for implies 1. Recently, Lima Pereira, Nuno Ballesteros, Orestes Okamoto, and Tomasella proved that if x0 is an isolated hypersurface singularity, then LCX is Cohen-Macaulay. Then this implication is always true. Given phi a holomorphic map germ defined on Cn to Cp, and X anice is defined by phi, we consider f a function germ with isolated singularity defined on these ices, and our goal is studying Groy's theorem for f in this context, that is, for f defined on ices. For this, we need the integral closure, we need the Milnor number of f defined on ices, and we need to know root j. For the integral closure, we will use the following characterization proved by Tessier. Let Y be a germ of analytic variety and I an ideal in this local ring. Then Tessier proved that the following conditions are equivalent. 8 belongs to the integral closure of I if and only if for each system of generators A1 until 8R of I, and for each analytic curve gamma defined on C to Y, the usual valuation of 8 composed by gamma is greater than or equal the infamous of the usual valuation of all generators of I composed by gamma. Now we will define the Milnor number of the function f defined on ices. For this, we consider the deformation of phi, capital Phi, defined by capital Phi of Sx equals phi Sx, such that when s equals 0, we obtain the initial phi. Some notations: capital X equals capital Phi minus 1 of 0, and xs equals phi s minus 1 of 0. We assume that xs is smooth for s sufficiently small and different of 0. We consider a holomorphic function germ f tilde defined on capital X, such that for all s sufficiently small and different of 0, the germ fs defined on xs is a Morse function. We consider B a small enough ball centered at the origin in C times Cn, and we consider capital Phi defined on B. So we have a representative of x0. This representative is capital X equals capital Phi minus 1 of 0. Then we have our representative of f tilde. This representative is f tilde defined on X, capital X, where capital X is the representative of capital X0. Then we define the Milnor number of f by the number of critical points of Fs. We consider D the set of points Sx belongs to capital X such that X is a singular point of Fs. Then we consider the projection P defined on D such that P of Sx equals S. Then the Milnor number of f is the degree of P. And by Mumford, the Milnor number of f is the Hilbert-Samuel multiplicity of the ideal generated by S with respect to this ring. Since this ring is Cohen-Macaulay, then this multiplicity equals this dimension. Then the Milnor number of f equals this dimension, and since this local ring equals the On plus 1 over the ideal generated by capital Phi, then this dimension equals this dimension, and this dimension equals the dimension of On over the ideal generated by Phi plus the ideal generated by the maximal order minors of the Jacobian matrix of F and Phi. Now, by Legroy's formula, we have that this dimension is the Milnor number of X plus the Milnor number of X intersection of F minus 1 of 0. Now, we consider a flat deformation of F such that Ft of 0 equals 0. Then we say that capital F is mi constant if the Milnor number of F equals the Milnor number of Ft for t sufficiently small. Now we talk about the ideal J. We remember that the J of Groyle is the ideal defining the singular set of each germ Ft defined on Cn. The similar way, Rj is the ideal defining the singular set of Ft, where Ft is defined on Isis. That is, Rj is the ideal generated by the maximal order minors of the Jacobian matrix of G, where G is the application Phi and capital F tilde, where capital F tilde restricted to C times X equals capital F. I forgot to say, we will denote Rj by Jg. Then the assertions of Groyle's theorem in this context are: 1. Capital F is mi constant. 2. For every holomorphic curve gamma defined on C to C times X, the usual valuation of partial derivative of capital F with respect to t, composed by gamma, is greater than the infimus of the usual valuation of all generators of Jg composed by gamma. 3. The usual valuation of partial derivative of capital F with respect to t composed by gamma is greater than or equal the infimus of the usual valuation of all generators of Jg composed by gamma. 4. Partial derivative of capital F with respect to t belongs to the integral closure of the ideal Jg. 5. Partial derivative of capital F with respect to t belongs to the radical of Jg. And the last item, the variety of Jg equals C times 0, where the variety of Jg is the set of points Tx belongs to C times Cn, such that all generators of Jg in these points equal 0. Unfortunately, these assertions are not equivalent, but we prove the following result. Now we will present an idea of this demonstration. 2 implies 3 is trivial because if this valuation is greater than this, then this valuation is greater than or equal this. For 3, if and only if 4, we use the characterization for the integral closure proved by Tessier. 4 implies 5 is true because the integral closure of an ideal is contained in the radical of this ideal. For 1, if and only if 6, we use the principle of conservation of the Milnor number. To finalize the idea of your demonstration, we now prove that 6 implies 5. By hypothesis, the variety of Jg equals C times 0. Besides, our deformation is such that Ft of 0 equals 0. Then Ft belongs to the maximal ideal of On. Then the capital F of Tx equals x1 g1 tx plus until plus xn gn of tx, where gi of tx belongs to on plus 1 for I equals 1 until n. Then the partial derivative of capital F with respect to t equals x1, the partial derivative of g1 with respect to t, plus until plus xn, partial derivative of gn with respect to t. So when see for the partial derivative of capital F with respect to t restricted to the variety of jg, then it is equal 0 because by hypothesis the variety of jg equals c times 0. Then x1 equals 0 until xn equals 0. Then the variety of jg is contained in the variety of the partial derivative of capital F with respect to t. Then by Hilbert-Nussbaum theorem, we concluded that the partial derivative of capital F with respect to t belongs to the radical of jg. Now, to finish, I will present a counterexample. We consider x an ice is defined by x4 minus y3, and f equals x, and we consider the deformation of f defined by x plus ty. Then in this context, Rj or Jg is the ideal generated by 3y2 plus 4tx3. And we consider gamma defined by 0, S3, and S4. Then the usual valuation of partial derivative of capital F with respect to t composed by gamma is the usual valuation of y composed by gamma. That is the usual valuation of S4, that is equals 4. And the usual valuation of the generator of Jg composed by gamma is the valuation of this composed by gamma. And since t equals 0, this valuation equals the valuation of y2 composed by gamma. That is 2 times 4 equals 8. Then 2 and 3 are not true, because in 2 this valuation is bigger or is greater than this, and in 3 this valuation is greater than or equal this. For the other hand, 1 is true, because Nuno Ballesteros, Orefsio Kamoto, and Tomasella proved that if we have an weighted homogeneous and F a function germ with isolated singularity, weighted homogeneous with the same weights of the ices, then all non-negative deformations has constant Mueller number. And in our case, our ice is weighted homogeneous with weights 3 and 4. And our deformation is a non-negative deformation of F, because y has weight degree 4 and x has weight degree 3. And since our deformation is a non-negative deformation, then by Nuno Ballesteros, Orefsio Kamoto, and Tomasella, we have that the Mueller number of F is constant, then 1 is true. Therefore, 1 implies neither 2 nor 3. Here some references that I used in my presentation. More references. Thank you.